In this module, we explore the Carnot cycle, a fundamental concept in thermodynamics that defines the limits of efficiency for heat engines. We will cover the key processes involved, the calculation of work and efficiency, and discuss some theoretical and practical implications of this model. As we have discussed previously, the maximum work output in a cyclical thermodynamic process, such as one taking place in heat engines, is obtained in a reversible cycle. Therefore, we focus on calculating the efficiency of a reversible heat engine, as this represents the theoretical upper limit of efficiency for any real engine. A reversible heat engine converts heat into work by utilizing the natural tendency of heat to flow from a hot reservoir to a cold reservoir. The reversible process in such a reversible heat engine is known as the Carnot cycle, named after the French engineer Sadi Carnot, who was the first to study such cycles in the early 19th century. The Carnot cycle consists of 4 stages in which the working substance, typically an ideal gas, undergoes a sequence of reversible expansions and compressions in a specific order, allowing the engine to perform work on the surroundings. The Carnot cycle, also known as the Carnot process, was not described in details by Sadi Carnot himself. While Carnot introduced the concept of a reversible heat engine in his 1824 work Réflexions sur la puissance motrice du feu, he did not provide a complete thermodynamic description of the cycle. It was later in 1834 that Benoit Paul-Émile Clapeyron expanded on Carnot's work by providing a more detailed mathematical analysis of the Carnot cycle. Émile Clapeyron was a French engineer and physicist whose career was deeply rooted in mathematics and engineering. He is known for his significant contributions to physical and mathematical theory, as well as for his work in practical engineering and particularly in the field of thermodynamics. After graduating from École Polytechnique in 1820, Émile Clapeyron spent a decade in St. Petersburg teaching mathematics and advancing mechanical engineering. Upon his return to France in 1830, he became a key figure in the emerging railway industry. He was designing and constructing major railway lines, as well as teaching at various academic institutions. His combined focus on theoretical principles and practical applications enabled him to innovate in fields ranging from railway engineering, where he improved the efficiency of steam engines, to thermodynamics. Clapeyron's keen mind embraced the complex problem of how mechanical work is produced, especially in steam engines where there is a direct correlation between the amount of work generated and the amount of coal consumed. The question of how this mysterious transformation occurs intrigued him, a question that had intrigued only a few scholars before him. He had the good fortune to come across a small booklet that was, at the time, little known but would later become famous due to his efforts. Réflexions sur la puissance motrice du feu by Sadi Carnot. Struck by the depth and accuracy of Carnot's ideas, Clapeyron thoroughly studied the work, absorbed its essence, and expanded upon it in a groundbreaking account that marked a significant milestone in the history of science. In his 1834 paper Mémoire sur la puissance motrice de la chaleur, Memoir on the Motive Power of Heat, Clapeyron drew attention to the ideas of Carnot, who had died 2 years earlier, by further developing them and presenting them in a more accessible form. In doing so, he brought Carnot's work to the attention of the scientific world, helping to lay the foundations for what would become thermodynamics. While the concept of the Carnot cycle originated with Sadi Carnot, it was through Clapeyron's development that we gained the comprehensive description and mathematical framework of the Carnot process. Carnot had developed a compelling analysis of a generalized heat engine, but he relied on the clumsy and increasingly outdated caloric theory. Sadi Carnot's work was virtually unknown before Clapeyron's paper. Clapeyron, in his memoir, highlighted the novelty and importance of Carnot's ideas. He expanded on Carnot's ideas on heat and provided a clearer mathematical formulation of them. He described the Carnot cycle using isothermal and adiabatic processes, which involve both heat exchange and work done by the system. Carnot's ideas were presented in a more accessible form using analytical methods and graphical representations. Clapeyron depicted the Carnot cycle as a closed curve on an indicator diagram. The indicator diagram, also named in his honor Clapeyron's diagram, is a chart of pressure against volume. Clapeyron's analysis of Carnot's ideas was more broadly disseminated in 1843 when Johann Poggendorff translated his memoir into German. This work significantly influenced William Thomson, Lord Kelvin, and Rudolf Clausius when its importance for the second law of thermodynamics became evident. Clapeyron further developed the idea of a reversible process already suggested by Carnot. In 1843, he made a definitive statement of Carnot's principle, what is now known as the second law of thermodynamics. The reversible Carnot cycle is illustrated in the pressure-volume diagram shown in this figure. The cycle involves four distinct reversible processes where a gas, acting as the working substance, undergoes expansion or compression in a specific sequence. These steps are designed so that the engine returns to its initial state after completing all four stages. Specifically, the Carnot cycle involves two isothermal and two adiabatic processes. In the isothermal processes, the gas exchanges heat with a hot or cold reservoir while maintaining a constant temperature. In the adiabatic processes, there is no heat exchange with the surroundings, and the system's temperature changes as it expands or compresses. For simplicity, we consider an ideal gas as the working substance undergoing these steps. The first step of the Carnot cycle is an isothermal expansion. In this stage, the heat engine is connected to a hot reservoir at temperature T hot. The gas absorbs heat from the hot reservoir, causing it to expand. As it undergoes a reversible isothermal expansion from point A to point B in the PV diagram, the gas does work on the surroundings while maintaining a constant temperature T hot. In the second step, the piston is disconnected from the hot reservoir and the gas undergoes an adiabatic expansion. Unlike the first step, where the temperature remained constant, there is no heat exchange with the surroundings during this adiabatic process. As the gas expands from point B to point C in the PV diagram, it continues to do work on the surroundings. However, since no heat is transferred in or out of the system, the temperature of the gas decreases. By the end of this adiabatic expansion, the gas has cooled from T hot to T cold. In the third step, the gas comes into contact with a cold reservoir and undergoes an isothermal compression from point C to point D in the PV diagram. During this isothermal process, the surroundings perform work on the gas and the gas releases energy as heat to the cold reservoir at T cold. The temperature remains constant at T cold throughout this compression. The final step is an adiabatic compression, where the gas is isolated from any heat reservoir. During this step, the gas is compressed from point D back to its initial volume at point A on the PV diagram. Since the process is adiabatic, there is no heat exchange with the surroundings. The surroundings do work on the gas, causing its temperature to rise back to the initial temperature T hot. This completes the Carnot cycle, bringing the system back to its initial state. In summary, during the Carnot cycle, heat is absorbed by the engine from the hot reservoir at T hot during the isothermal expansion first segment and is released to the cold reservoir at T cold during the isothermal compression third segment. Work is performed on the surroundings in the first two segments during the isothermal and adiabatic expansions and on the system in the last two segments during isothermal and adiabatic compressions. Remember that the area enclosed by the cycle on the PV diagram represents the net work done by the engine. For the engine to be practical, it must do work on the surroundings. According to the thermodynamic sign convention in the first law of thermodynamics, the net work done by the engine in the cycle is negative when the engine performs useful work on the surroundings. This occurs when the absolute amount of work done during the expansion phases is greater than the work done during the compression phases. The efficiency of the Carnot engine is determined by comparing the net work done per cycle to the heat absorbed from the hot reservoir. Before calculating the efficiency of the Carnot cycle, let's try to understand why it is designed in its specific form and why it is considered reversible. The key feature of the Carnot cycle is the use of alternating isothermal and adiabatic processes. The isothermal segments ensure that heat is absorbed from the hot reservoir and released to the cold reservoir in a reversible manner, with the temperature remaining constant in both cases. The adiabatic segments are crucial for changing the temperature of the gas while preventing the irreversible exchange of heat with the surroundings. This design ensures that all heat exchanges occur at specific temperatures, allowing the cycle to be reversible and maximizing its efficiency. The efficiency of the Carnot cycle can be determined by calculating the heat exchanged, the work done, and the change in internal energy for each segment of the cycle. For these calculations, we assume that the working substance with the amount of substance N behaves as an ideal gas with the molar heat capacity at constant volume CVM. In the first step, we have an isothermal reversible expansion of the gas from volume VA to VB at a constant temperature T hot. This is the highest temperature in this process, corresponding to the hot reservoir. During this isothermal expansion, the gas does work on the surroundings and absorbs heat from the hot reservoir. Because the temperature remains constant in an isothermal process, the internal energy of the ideal gas does not change. Therefore, the change in internal energy delta U1 equals the work done by the system W1 plus the heat absorbed Q1, and this equals 0. This means that the work done by the gas in step 1 W1 is equal to the negative of the heat absorbed from the hot reservoir Q1. For an ideal gas undergoing isothermal expansion, the work done by the system W1 equals negative N times the gas constant R times the T hot times the natural logarithm of the ratio of the volumes VB to VA. Since the heat absorbed Q1 equals negative W1, it is given by N times R times T hot times the natural logarithm of VB divided by VA. The second step in the Carnot cycle is a reversible adiabatic expansion of the gas from volume VB to VC. During this process, the gas continues to expand and work W2 is done on the surroundings. However, unlike the first step, there is no heat exchange with the surroundings because the process is adiabatic. As a result, the temperature of the gas decreases from the temperature of the hot reservoir T hot to that of the cold reservoir T cold. According to the first law of thermodynamics, in an adiabatic process where no heat is exchanged, Q2 is 0, the change in internal energy of the system, delta U2, is equal to the work done by the gas, W2. The work done during this reversible adiabatic expansion can be calculated by considering the change in internal energy, which depends on the amount of substance of the gas, its molar heat capacity at constant volume, and the temperature change from T hot to T cold. N times CVm multiplied by the difference between T cold and T hot. This step results in the gas cooling down to the temperature of the cold reservoir T cold while performing work on the surroundings. The third step in the Carnot cycle is an isothermal reversible compression of the gas from volume Vc to Vd, occurring at the constant temperature of the cold reservoir T cold. During this step, heat is released from the system to the cold reservoir at T cold. The surroundings perform work on the system, causing the gas to compress. In an isothermal process with an ideal gas, the internal energy change, delta U3, is zero because there is no change in temperature. Consequently, the heat released Q3 is equal to the negative of the work done, W3. The work done, W3, is given by negative N times R times T cold times the natural logarithm of Vd divided by Vc. And the corresponding heat released to the cold reservoir, Q3, is N times R times T cold times the natural logarithm of Vd divided by Vc. In this process, the work is positive because the surroundings do work compressing the system and reducing the gas volume from Vc to Vd. The heat released from the system to the surroundings is negative. The fourth step in the Carnot cycle is a reversible adiabatic compression, where the volume of the gas decreases from Vd to Va. During this adiabatic compression, work W4 is done on the system by the surroundings. The temperature of the gas increases from T cold to T hot. Since this process is adiabatic, there is no heat exchange with the surroundings. According to the first law of thermodynamics, the change in internal energy of the gas, delta U4, is then equal to the work done on the gas, W4. Therefore, the work done during this adiabatic compression, W4, equals N times CVm multiplied by the difference between T hot and T cold. All in all, in this adiabatic compression step, the work performed on the gas increases its temperature back to T hot, which completes the Carnot cycle by returning the gas to its initial state. The total work done by the Carnot engine during one complete cycle corresponds to the area enclosed by the cycle on a pressure-volume diagram. This work is the sum of the work done in each of the four steps of the cycle. However, the net work done during the adiabatic steps 2 and 4 is zero. As a result, the total work done by the cycle is determined only by the work done during the isothermal steps 1 and 3. Let's now examine the adiabatic processes in the Carnot cycle more closely. In a reversible adiabatic process, the temperature T and volume V are related by the equation T times V raised to the power of gamma minus 1 is constant. Alternatively, we can express this as V times T raised to the power of 1 over gamma minus 1 is constant. This relationship holds for both adiabatic steps. For the second step, an adiabatic expansion from Vb to Vc that cools the gas from T hot to T cold, the relationship is Vb times T hot raised to the power of 1 over gamma minus 1 equals Vc times T cold raised to the power of 1 over gamma minus 1. For the fourth step, an adiabatic compression from Vd to Va that warms the gas from T cold to T hot, the relationship is Vd times T cold raised to the power of 1 over gamma minus 1 equals Va times T hot raised to the power of 1 over gamma minus 1. If we multiply these two expressions, we obtain Vb times Vd times T cold raised to the power of 1 over gamma minus 1 times T hot raised to the power of 1 over gamma minus 1 equals Va times Vc times T cold raised to the power of 1 over gamma minus 1 times T hot raised to the power of 1 over gamma minus 1. When we cancel out the temperature terms on both sides of the equation, we simplify these to Vb times Vd equals Va times Vc. This can be reformulated as the ratio of Vb to Va equals the ratio of Vc to Vd. This means that the volumes Va, Vb, Vc, and Vd are not independent in this process. They are interrelated by the above equations. This interdependence of vertices is a key feature of the Carnot cycle. We can now simplify the expression for the total work done in the Carnot cycle. The total work done in the cycle is equal to negative n times r times T hot times the natural logarithm of Vb over Va minus n times r times T cold times the natural logarithm of Vd over Vc. This can be simplified to negative n times r times the sum of T hot times the natural logarithm of Vb over Va and T cold times the natural logarithm of Vd over Vc. By using the derived relation between gas volumes in points A, B, C, D, the expression simplifies further to negative n times r times the difference between T hot and T cold times the natural logarithm of Vb over Va. This final form shows that the total work done in the Carnot cycle is proportional to the temperature difference between the hot and cold reservoirs and the logarithm of the volume ratio Vb to Va. Since T hot is greater than T cold and Vb is greater than Va, the total work has a negative sign, indicating that net useful work is performed by the system during the Carnot cycle. Now let's discuss the efficiency of the Carnot cycle. The heat absorbed by the system from the hot reservoir during the isothermal expansion can be expressed as N times R times T hot times the natural logarithm of Vb over Va. The efficiency eta is the ratio of the absolute value of the net work done by the engine to the heat absorbed from the hot reservoir. Substituting the expressions for total work and absorbed heat into this equation, we find eta equals the difference between T hot and T cold divided by T hot, which simplifies to 1 minus T cold divided by T hot. This shows that the efficiency of the Carnot cycle depends only on the temperatures of the hot and cold reservoirs. There is a common misunderstanding related to the efficiency of the Carnot cycle. On one hand, according to one formulation of the second law of thermodynamics, the Carnot cycle has the highest efficiency for any process operating between two temperatures. On the other hand, we know that for any cyclic process, the total work done is equal to the total heat exchanged with the surroundings. This simply follows from the first law of thermodynamics. The work done in a cycle is equal to the heat exchanged in that cycle. So, what does this mean? Does it imply that the efficiency is 100%? Of course not. The efficiency is not 100%, and the reason is as follows. The efficiency of a heat engine is defined as the ratio of the work done in the whole cycle to the heat absorbed. In the Carnot cycle, not all the absorbed heat is converted to work. Some is inevitably lost to the cold reservoir. This is the reason why the efficiency is always less than 100%. In the Carnot cycle, there are two processes where heat is exchanged with the surroundings. One during the heating and one during the cooling. When the system cools down, the released heat is simply considered a loss and is not accounted for in the efficiency of the engine. If we rearrange the terms in the definition of the efficiency of a heat engine a bit, we get the following expressions. Here, the efficiency is equivalent to the heat added during the heating plus the negative heat removed during the cooling, divided by the heat added. Note that this is a theoretical definition of efficiency. This formula shows again that the efficiency of the Carnot cycle is always less than 100% because some heat is inevitably lost to the cold reservoir. Let's take another look at the formula for the efficiency of the Carnot cycle. You can see that the efficiency of the Carnot cycle depends on the temperatures of the hot and cold reservoir. Specifically, the efficiency increases when the temperature of the cold reservoir decreases and when the temperature of the hot reservoir increases. In other words, the higher the temperature at which heat is supplied and the lower the temperature at which heat is rejected, the more efficient the cycle becomes. Now, when could we theoretically achieve 100% efficiency? This would happen if the ratio of T cold to T hot approaches zero. There are two theoretical ways this could happen, either by having the temperature of the hot reservoir become infinitely high, or by having the temperature of the cold reservoir reach absolute zero, which is 0 Kelvin. While having an infinitely high temperature for the hot reservoir is not practically achievable, let's explore the second option more closely. If the cold reservoir could reach 0 Kelvin, the efficiency would indeed be 100%, as all the heat absorbed could be converted into work. However, without going into detail, I note that according to another principle of thermodynamics, reaching absolute zero is impossible. So, while the formula for the Carnot efficiency suggests that perfect efficiency could have been possible, it also brings us to the understanding that such a scenario is actually impossible. The inability to reach absolute zero is related to the principle that no heat engine, including the Carnot engine, can ever be 100% efficient. This is in line with the Kelvin-Planck statement of the second law of thermodynamics, which says that no process is possible whose sole result is the complete conversion of heat into work. Let's talk about how we can improve the practical efficiency of heat engines using a concept known as cogeneration. In theory, the efficiency of a heat engine is defined as the ratio of the work done to the heat absorbed. This theoretical definition assumes that the heat removed from the system during the cooling process is entirely lost. For example, in conventional power plants, the waste heat is typically released into the atmosphere. However, the efficiency of real-world systems can be significantly improved through innovative methods like cogeneration. This is a process where the heat that would otherwise be wasted is captured and repurposed for other uses, such as heating water for buildings. In this figure, you can see an illustration of a cogeneration system. Natural gas is burned to fuel an engine, producing both electricity and heat. Instead of letting the heat escape as waste, it is used to heat water, which can then be circulated for heating buildings. In this way, we increase the overall economic and, importantly, ecological efficiency of the system beyond the mechanical efficiency of the heat engine alone. Cogeneration is particularly useful in urban areas, where the proximity of power plants to buildings minimizes the loss of heat during transportation. By using the waste heat for local heating, we reduce the total fuel consumption required for both electricity and heat production.